All right, Atlas, welcome back. This is second part of Essential Topics Part 1. This is Part 2 of Essential... rewind. Let's leave that in there. Welcome back, Atlas. This is Essential Topic 1, Part 2, Equilibrium of Particles in 2D and 3D, and today we're answering the question, what problems do I need to know how to solve in order to nail these quizzes? Okay. So, last week we resolved vectors into x and y. This week we are going to identify the directional unit vector lambda AC, or lambda sub AC. Okay, AC doesn't really matter what letters they are, as long as they're from the first point to the second point. That's how we come up with those, but AC can be any two letters. Okay, so that's going to be the big crux of the second problem today, is identifying the directional unit vector. Let's get into it. This is the problem we did last week. This is what we're going to jump into this week. Okay, and so the problem statement says, compute the tension TAD, knowing that TAC is 1347 pounds. Okay, and then we need to recall that lambda AC is equal to the position vector from A to C, divide that by the length of AC. Okay, those are things we need to keep in mind. All right, let's go top down, where I have my picture drawn out for us already. The only things I don't have filled out here yet are my known table and my want table. So what is known based on the problem statement, we know that TAC is equal to 1347 pounds. And it doesn't give us any weight or load. So that's the only known thing we got. And we want TAD. And since we're in pounds, we know we're going to report something in pounds. Nice little reminder of where we're going. Okay, this is complete. Do a little bit of labeling here. So this is quiz 1, example 2. And step 1, free body diagram. I'm always a big proponent of labeling your steps. Okay, step 1 in statics, I don't know how many problems don't start with free body diagram, but it's very, very, very little. Okay, so let's start with a free body diagram at, do we have that point labeled? It is, it's called A. Free body diagram at A. And I warn you now that when you go from a three-dimensional problem into a two-dimensional representation of that problem, it's going to look a little bit funny, but bear with me. We just want to draw out the free body diagrams to see what we're working with, get our variables out and communicate them to our reader. Okay, so we're going to have our point A here, and let's start filling in our things that pull on the point A. So first, if not the most important, is going to be our load. Okay, L for load. It doesn't tell us how much anything weighs, but we have something pulling down. A crate, a box, a pallet of bricks. It doesn't really matter what it is, but it's going to be pulling on a singular point marked at A. Okay, first we have a vector from alpha to Bravo. So I'm going to label this tension alpha Bravo. Okay, and the subletters just mean it comes from A, it originates at A, and goes to B. Okay, next one is going to be TAC. That's the one we know. So we know the tension in this force is going to be 1347 pounds. Okay, last but not least, the tension from alpha to delta is off somewhere over here. Okay, see what I mean? This 2D representation of a 3D model doesn't really make sense, but it gets all of our cards on the table. Okay, now what? Now what are we going to do? So the big crux of this problem is using lambdas appropriately. So let's go ahead and define our lambdas. Okay, let's start with lambda AD. Recall that it's going to be position vector over the magnitude of the vector. So we should have something like that. And from alpha to delta, I'm going to look at A, and I'm going to be standing at A, and I want to know what is the path in X, Y, and Z that it takes me to get to delta. Okay, so if I'm standing at alpha and I want to go to delta, I'm going to go against the positive direction at A, or positive direction of X, a distance of 24 inches. So this is 24 inches, X hat, but from A to D, we're going this direction, which disagrees with our positive convention here. So this means this receives a negative. Okay, that's X. Now, if we're standing at A and we want to go to D in the Y direction, we're going to go up a distance of 50 inches. Okay, and since we're at A and we're going to D, we're going to go up. Up is positive Y, so that's going to receive a positive Y hat. And now finally in the Z direction, from alpha to delta, we're going to be going a distance of 20 inches. Z hat. And we will be going essentially from the origin in the positive direction of Z, so that will also receive a positive. Okay, pretty simple. By inspection, we figure that out. Now we're going to, oops, that's not what I want. We're going to clear this off, and we're going to do the magnitude calculation. So 24 squared plus 50 squared plus 20 squared equals 58.9. inches. Okay, so that's lambda AD. And remember that lambda is equal to, that's not right. It's not the lambda. I guess I have to put subs in here. Let's do mn though. Over the magnitude of m n. Okay, just so we're aware of what we're doing. Okay, next we'll move on to lambda AC. Okay, so from A to C, how far are we going in the x direction? Well, C looks coplanar with the YZ plane, which means we're going 0 in the x direction. So 0 degrees x hat. In the y direction, we're going to be going up the same 50 inches that we went in AD. And in the z direction, we're going essentially from the origin away from Z, positive Z, a distance of 25 inches. Okay. And the length of this will be the square root of 50 squared plus 25 squared. 55.9. I'm going to go ahead and call that 56. Actually, no, let's keep the numbers legit. 55.9 inches. And last but not least, lambda AB. Okay, this should be pretty simple for you now. We've done 2 examples already from A to B. So from A to B in the x direction, we're going a distance of 30 inches. Okay, and we're going to be going from A to B in the positive x direction, right, down to the right. So that'll receive a positive. Y is going to be the same, plus 50 inches that we had in the other 2. And the z direction, well, we don't have any z direction here because B is coplanar in the y and x axis. So we don't have to move any in the z. Say we got a couple zeros there. And the length of alpha bravo will be 30 squared plus 50 squared, 58.3 inches. Okay, now what? We got our lambdas in play. We have a free body diagram that looks terrible in 2D. Now what? Okay, now I'm going to draw a little divider on my paper so we can go on to step number 3. And now we want to define the vectors TAD, TAC, and TAB. We want to define tension vectors, right? Because these two are only magnitudes. We just know the tension in each one of them. What this does when we get a harpoon on the top is we want to know how much push or pull do we have in X, Y, and Z. Okay, and so if we know how much push or pull we have in X, Y, and Z, now we have a vector. This is only a scalar. It's only a number. 1347 pounds. 1347 pounds in what direction? Where? What is it doing? Is it just sitting on the floor? Is it an X, Y, Z? So if it has no direction, it is not a vector. Okay, so in order to get our vectors, we're going to have to define the tension vector equal to the magnitude of the tension, multiply that by lambda. Because lambda will tell us how much in each direction. Okay, so let's go ahead and start that with TAD vector is going to equal TAD, the magnitude, this answer is right here. Okay, and then we're going to multiply that by, and I'm going to go ahead and break these up into X, Y, and Z components. It's going to be more beneficial later, so let's go ahead and do that now, where we have negative 24 over 58.9. And this is inches over inches, so I'm going to leave this unitless. This should be pounds, right? So inside of AD is the unit pound. So we'll have this vector, pounds in X, pounds in Y, pounds in Z. That's how we know it's a vector. Okay, so this is all X hat. Minus carries over. Plus 50 over 58.9. Y hat. Plus 20 over 58.9 Z hat. Okay, let's just rinse and repeat. Do this twice more with TAC. We have 0 X hat. Positive 50 over 55.9. Y hat. Minus 25 over 55.9 hat. And TAC, we actually know. We have this value, so we can compute these two values and have numbers here with no variable inside of it. So that's good to know. And last but not least, we'll go to TAB. $30 over 58.3 plus 50 over 58.3. Right. Okay, good. Now what? Now what can we do? We can stick a number in here and get this value out. So let's go ahead and do that, because that's probably what I would do next as a student. So TAC is equal to 1347 pounds times 0 is still 0 X hat. Does this make sense? Yes. So how much does the vector TAC pull in the X direction? Look, it pulls none. It doesn't pull this way or this way. It's coplanar. So this makes sense that we've gone this far. And now let's do 1347 times 50 divided by 55.9. Plus 1204 Y hat. Units on this will still be pounds. Okay, and then 1347 times 25 divided by 55.9. Minus gets retained. 602.4 pounds z hat. Okay. Now what? Now what can we do? Now we're gonna pull something out of, I think, algebra 2. I don't know where it gets introduced from, but I should find that out. And what we're gonna do now is introduce. We're going to integrate a mathematical approach called equating coefficients. Okay, and what this means is we're going to take all of the x equations, set them equal to 0. Take all the y equations, set them equal to 0. And take all the z equations, set them equal to 0. Okay, that's what this means. So all of the x equations are going to be here. And so when I do this, I'm going to drop off the x hat because I'm only dealing in the x direction. This is the x equation. So we have negative 24 over 58.9 TAD. We have 0 TAC. And we have 30 over 58.3 TAB. Okay, that completes all of our x equations, so set that equal to 0. Y equations. We're going to start again with TAD. And we will have 50 over 58.9 TAD. TAC will be plus 1204 pounds, right? TAC, we already destroyed that variable and put it in there, so there's no longer a variable in this equation. Okay, and then last one, plus 50 over 58.3 TAB. And set that equal to 0, but then you'd be wrong. Okay? So here's what happens. When you equate coefficients, you take all of the forces in the x, the y, and the z, and we've been under the impression that they're all coming from this table. Yes and no. They're all coming from this table, but we're also missing a force not present in this table because we didn't define a lambda for it, and that would be the load. Okay, the load is pointing straight downward. Sometimes we forget, but this load, since it's traveling in the y direction, has to be incorporated into this equation. Has to be there. Okay, otherwise this is incomplete and you'll get some false answers. So, in the y equation, I'm going to introduce a load. Is that load positive or negative? Well, load is pointing downward, positive y is pointing upwards, therefore this should be negative load. Okay, now let's go on to the z equations. That'll be 20 over 58.9 TAD, negative 602.4 pounds, plus 0 TAB. Set that equal to 0. Perfect. Now what? Now what are we going to do? Okay, now I'm going to pull on my linear algebra skills, and I'm going to take this x, y, and z, linearly independent equations, and I'm going to stick it in a matrix, and I'm going to put it in row-reduced echelon form. Okay, so let's do that right here. Okay, I got to make some choices. First column is definitely going to be TAD. Next column should not be TAC because these are constants and destroyed. So I'm going to leave those alone for right now. That'll be these three guys here. 0 TAC, 1204, and negative 6204. So next one I'm gonna go on to is TAB. Load is also a variable, so I'm gonna stick that one in there. And that equals constants. Okay, so I'm gonna draw my matrix here now. Okay, if you're unfamiliar with how matrix forms work, this here is where all your variables go. This line is the equal sign, and everything on the right hand side is going to be our constants, which I've drawn as a C. Okay, so let's take all of this information and transfer it into our matrix. So if I factor out TAD, I will be left with negative 24 over 58.9. 50 over 58.9 and 20 over 58.9. Okay, that takes care of all the TADs. We'll skip over the TACs for now. We'll move on to TAB, which would be 30 over 58.3, 50 over 58.3, and 0. Okay, last column I need to deal with is my load column. There is no load in X or Z, so those both receive zeros. And there is a -1 that I pull out of load, right? Because if I have negative L, I can factor out a -1, and then I'm just left with L. That's what's happening here. Okay, now let's deal with the constants. Do I have any constants in the first equation that I could pop over to the right-hand side? I don't. All that equal to 0. Okay, do I have any constants that I can flop over to the right-hand side? I do. This 1204 is positive, so on the right-hand side, it'll become negative 1204. And I have a negative 602.4 here. Over the equal sign becomes positive. And now I'm able to put this into my calculator. Okay, so old and dusty TI-84 Plus, there's probably much better calculators out there on the internet. This is just how I do it. So I'm gonna go ahead and grab second matrix. I'm gonna edit a matrix, and this is gonna be 3 rows by 4 columns. So 3 by 4. Good. And now in each one of these cells, I'm going to pop in one of these numbers. This will be negative 24 divided by 58.9. I'm going to go a little bit slow here because I ruin these often. So on the video, it'll be forever cemented that I fat fingered something. Anyways, 30 over 58.3. 30 divided by 58.3. 0, 0. 50 divided by 58.9. 50 divided by 58.3. -1. Negative 1204. Okay. 20 divided by 58.9. 0, 0. 602.4. Okay, this now has my edited matrix that is called A. So I'm going to quit out of here. I'm going to go back into my matrix math. I'm going to select math and go to a function called RREF. When I press enter, the calculator says, hey, you have a function RREF, open parentheses. I need an argument to row reduce echelon form something. So the argument I'm going to give it is my the name A, the 3 by 4 matrix that I just edited. This flask. Anyways, RREF that, and I pop out with a couple answers. Okay, so let's interpret what this says. You're a little rusty on your linear algebra. What this says is, you grab a different color. results. Sidebar, you don't really need to do this, but I'm going to have TAC there, TAB, load, this is how I see this. Okay, the ones just tell me that the first row, first column is TAD, because that's what I pulled out here. And that answer is equal to 1774. So 1774 pounds. That's the answer. Boom, we done. Okay, it also, let's do a nice to know table. Because now we've solved the problem. We've answered the question, we can move on. But if I'm gonna sit here and I'm gonna learn, let's also fill in these other guys here. So TAB and load. So TAB is going to equal 1404 pounds, and the load is 3914 pounds. That's what happens when you get this matrix, stick into a calculator, you perform the row reduced echelon, you put the matrix in row reduced echelon form, and this pops out. This is how we interpret the results. And ultimately, this is my answer. That's what I'm going to report, 1774, because that's what the question asked for. So, if there are any questions, you can put them down in the comments down below. Hope you've had a great time. I hope you learned something. If not, we come to the video where I ask you for a subscribe, a comment, a like, anything you want. But yeah, you should check out, is it over there? Check out the playlist over there where I'll link something or have some card at the end. Anyways, that's all from me. My name is Joseph Rodriguez, aka Presser Panda. See you later. Bye bye.